Cool. Welcome, everyone. I'm Drew. I'm the founder of Webb. We're building a zero-knowledge messaging layer to enable things such as private bridges and the applications you can build on private bridges. And we focus a lot on the application space, so hopefully we'll get to that by the end of this talk. And we'll talk a bit mostly about some of the infrastructure that we're building and the ideas that underpin it. So the title of the talk is Cross-Chain Zero-Knowledge Messaging, and we're going to just jump in. So cross-chain zero-knowledge messages are quite similar to just cross-chain zero-knowledge proofs. So what are they, and why are we interested in them? Well, we want to prove or have the ability to prove statements from one blockchain to another. So here we have like a toy example. There's 4 blockchains. And Alice wants to interact with a smart contract on Ethereum. And maybe later she wants to prove knowledge of some state of Ethereum, but on Polkadot or on Polygon or Cosmos. And there's a yellow box around Alice because Alice can do this ideally in zero knowledge. She doesn't have to disclose her identity or sort of any information about the state on Ethereum that she doesn't want to disclose. Said in a slightly different light, Alice inserts a message into Ethereum or a bridge on Ethereum, and she proves knowledge of this message somewhere else. And if she does this in zero knowledge, an observer, Eve, will only learn whatever Alice wants to disclose. So that's sort of the idea that we're playing with here, is we want to send messages and we want to be able to prove properties about these messages across chain. From anywhere that a bridge is connected. Why are we interested in doing this? Well, we can do cross-chain proofs of identity. We can transfer assets across chain. We can do primarily all of this with privacy, so you don't need to disclose what you don't want to if you build zero-knowledge circuits the way to support that functionality. And something really nice about this architecture is that since you don't disclose information about your messages, specifically you don't need to disclose where those messages were inserted, you also get a scalable privacy set. So people can participate in this messaging system from potentially many different blockchains. And when they prove properties about their messages, they all sort of contribute to a shared privacy set. Some more complicated examples, and generally speaking, that we're interested in are doing even just scalable proofs of arbitrarily many statements about things happening on different blockchains. So maybe you want to prove about a batch of messages where those batches can grow arbitrarily large. How do we do this? The main way we do this is by connecting cryptographic accumulators across chains. So there's 2 sort of paradigms that we are interested in at Webb. Primarily the easy approach we've started on, which is by actually inserting messages into our own custom Merkle trees and connecting these Merkle trees across chains. But there's also the generic approach, where you can just use the underlying blockchain's trie and prove properties about multiple different tries. The reason the first approach is easy is because you get to roll your own Merkle trees. You can keep them all consistently structured. And the reason the generic approach is hard is because you might have to deal with different tries, different hash functions inside of a single circuit. It might get difficult to reason, or not reason, but to build a system that deals with a trie with Shah and a trie with Blake too, and so on, from 8 or 16 blockchains at once. So here's a diagram, or a little toy diagram of what this kind of looks like. We have Merkle trees that we put on all of these chains. And the standard zero-knowledge proof that we're interested in is a one-of-many membership proof. So kind of motivating it with that original example, if Alice were to insert a message on Ethereum, she would insert an element into the Merkle tree on Ethereum. And assuming we had some way of updating the root set everywhere, Alice would be able to go anywhere and prove knowledge of that message using a proof that proves she knows a message in one of many Merkle trees. And so that's sort of the basic primitive we're dealing with here. I'm focusing on Merkle trees because it's well known, but you can use any type of cryptographic accumulator or commitment scheme. But that's the general idea. And here's sort of how the paradigms are different. So in the message-driven method, we define a message. We hash that message with a zero-knowledge-friendly hash function. We insert it into a Merkle tree where we want to at least deposit that message to. We have some oracle that will update the state across chain, or we have some bridge. And eventually, we'll prove knowledge of that message in the set of roots. In the generic method, users are interacting with smart contracts, and that state is being updated across chain similarly as in the previous method. And in this one, we have to prove knowledge of state or receipts against the trie, so the state trie or the transaction trie and whatnot. And this is very general. It doesn't necessarily provide developers flexibility to customize applications as easily, but it's an open research area that we're investigating. Awesome. So hopefully that gives us the grounds for what we're mostly focusing on at Webb, which are the applications. So the first application that we've been interested in is an interoperable shielded pool or an interoperable private bridge. So you can think of this as a private transaction system that spans many different blockchains. Right now we're testing basically bridges between 8 different EVM chains, between substrate chains, potentially even Cosmos chains soon in the future. Yeah, and what does an application like this afford us? What allows us to build a single anonymity set across chain for shielded assets. So users can contribute to shared privacy for their ETH, for their stable coins, without even needing to bridge to other chains. They all sort of collaborate and create more privacy by participating in an interoperable shielded pool. Some examples of this would be like taking Zcash or Tornado Cash and making it also bridged. So we've built this on top of Webb as one of the motivating examples for all of this research and infrastructure. How does it look? It looks quite similar to Tornado Cash if people have, or really Tornado Nova, if people have interacted with that. This interoperable shielded pool is like a bridged UTXO system. So you generate UTXOs on the chain that you want to deposit to. Those are your messages in this messaging system. And you can generate proofs pretty similarly. We use Circom for a lot of this stuff and ArcWorks for the Rust-based chains. You generate proofs pretty quickly. The circuits aren't extensively large. And this is just a simplified API. Our APIs are still in work in progress, and we're improving them. But ultimately, you get a nice API where you can transact from one chain to another in a shielded pool. So in this example, we are both registering and transacting, similar to what you might have seen or known on Tornado Nova before it was removed from GitHub. Cool. A second application or set of applications that we're also now building are interoperable Semaphore sets. So these are membership sets or identity systems that span multiple blockchains. What this enables, similar to Semaphore if people aren't familiar, is the ability to do anonymous signaling. Now we can do anonymous signaling with members from any blockchain that are in this set, and we can run the polls on any of the connected blockchains. So we've taken the standard Semaphore system and sort of created it as a cross-chain system. It's nice because the anonymity set scales now across chains. You can sort of customize what you would, what you want your users of these Semaphore sets to, what properties you want them to have, whether it's they have to have like at least one token of a native balance, or to hold a specific NFT, or hold NFTs from different communities. And this will allow them to sort of group together without needing to be on the same chain. They can be in the same group. So some example applications we get from this are ultimately voting. We get social forums, and we get identity-based DeFi, which is sort of the next thing that we'll talk about. But first, to show you what examples of what the API looks like, it's exactly more or less the same as what Semaphore provides today. It's just that we now get to create polls, and people can generate proofs, potentially being members of the Semaphore set on some other chain, in order to vote on those polls. So I could be a member on Ethereum and run a poll on Polygon. And then everyone in this grouped this bridged Semaphore system can go vote on Polygon because it's cheaper there to generate or to submit these transactions. Yeah, so here's I'll give a few seconds just to look through it. We're identifying a group, adding a member, crafting a vote, and generating a proof and submitting it. And this is all sort of a bridged system. You can see in the generate proof function, we're passing in a root set. We're passing in roots. So these are roots of the many Merkle trees that define our bridged Semaphore system. The nice part about all of these tools is that they compose quite nicely with one another. You, at the moment, just have to write a new circuit. So something we're doing is taking those two example applications that we described, the shielded pool and the Semaphore system, and combining them. So we can build shielded pools that are bridged between chains, where in order to transact on them, you have to continue to prove every time you transact that you're also still a member of the Semaphore system. So people can create identity systems where they also allow those users to transact in a shielded pool. And this is fairly customizable. You just change something in your circuits. So if you want to, restrict users from who they create output commitments to, like transfers to, you can also restrict that those outputs are in the Semaphore set, and so on. There's a lot of flexibility here, and we're investigating this a lot, how we can compose these different systems. So here's an example of the API, similarly to before, of the shielded pool. We're going to create our inputs, our outputs, which are all destined for some chain to be spent on some chain. There's some nuance to it. We create some external data that we want our smart contract to deal with, and eventually we'll just generate our proof. But in this proof, for example, you also have to provide a proof that your identity is in the Semaphore set. Cool. So what are the future explorations that we're interested in? Yeah, we're at the moment trying to unify a system like this. So right now, every time we deploy one of these applications, it also comes with its own set of Merkle trees, which is a bit clunky. You have to basically roll a new tree for all the different message types that you have. So something we're investigating is whether we can use one set of trees for all of our messages. For all the users who want to deploy applications to a system like this, it'd be nice if they can use a single deployed set of Merkle trees. So we're investigating what you would need to take into account to support an application like this. It might be that you need application identifiers, or it might be that you also commit to the circuit that you want your message to correspond to, it similar to how ZK8 works. And so we're sort of exploring that too. That's the second point. One nice part of that line of work is that we can also start to unify our setups for our bridge systems. So we can venture more into like a ZK VM landscape, where maybe it's possible to deploy multiple different programs to this type of bridged system, where each message commits to the program that they're interested in. That's part of like the message itself. This would allow us to do user deployable applications and run one consistent set of infrastructure that doesn't blow up as the number of applications grow. And then finally, there's a nice and new interesting line of work by Sun. It's a GitHub project called Zka Tester, where we can start to do general state proofs in zero knowledge. So these are just proving state about, let's say, the Ethereum Merkle trie. And if we can sort of compose lots of these proofs, then we can do quite expressive and interesting things, like prove that you made a transaction with some property without disclosing whatever properties you don't want to disclose. So this goes back to the general messaging paradigm, but it's certainly of interest to us. But yeah, that's the talk. I hope there might be questions, but if not, thank you all for listening. This is some of our community links. We have a Twitter, it's at Webb Protocol. Our doc site is docs.web.tools, and our GitHub is GitHub at web/web-tools. My email's there if anyone wants to email me. We are hiring, so if you are a zero knowledge engineer, would be super interested to chat with you. And even if you aren't an engineer, I'd still be interested to chat with you. So thank you for listening. In the back.
For the kind of room set, is that done by kind of staking, or how is that updated?
This one?
Yeah.
At the moment, they're kind of, yeah, I would say some form of actually governance right now. So we have built a layer 1 that runs an on-chain governance process for connecting these smart contracts. So how to participate in those votes is effectively by bonding tokens. But yeah. Each of these right now, it's sort of like an ad hoc setup. You propose to link this system a priori to people using it.
But then the state of one blockchain is by rote, or it's by governance design. It's not that you verify, I don't know, proof of work or something like this.
Yeah, right now we are investigating doing basically one-way trustless light clients, but we do use a threshold signature network to sign these updates, primarily because it's extremely expensive to build bidirectional light clients and prove this state. So we wanted a cheap solution. Yeah, once you set a system like this up, you connect these smart contracts together. We can play around with the different trust models we want.
I have a question. I think then it's like a follow-up. So what's stopping this protocol from being used for building bridges? Is that the missing lifeline between the chains that you need?
So this system effectively becomes a bridge, if that answers your question. And that's sort of what our chain is providing, is message signing in order to bridge these systems together. It's sort of the missing piece, the missing like oracle that tells one end what the state of the other ends are. Is sort of the part that wasn't described in this talk. But yeah, we've built the infrastructure for doing the bridging, and we're exploring like how we can continue to decentralize that more and more. That answer your question?
Yeah, it does.
Okay. Go for it.
Just curious about like what's assets flowing from one chain to another in general, like in aggregate or anything like that?
Yeah, so at least for the interoperable shielded pool, in order to get assets into a system like this, you have to deposit them. So it could be that we have a 16-sided shielded pool on 16 different chains, but most of the liquidity was deposited on 3, and most of the withdrawals are happening on those same 3. So there's certainly, some metadata that you can infer from the usage of the system. And it'd be interesting, we explored this in the past, how we might incentivize like distributing liquidity evenly across a system like this, because that might provide the most privacy. But you're right, what other sorts of privacy might be exposed? There's certainly like traditional, as is traditional with Tornado Cash and et cetera, like how quickly you transact through a system like this will kind of dictate your privacy. And certainly at the RPC level, like how you are making your proofs. So if you ask an RPC node for, your witness data, you'll tell that node what transactions you're spending.
Could any of this sort of metadata be used to detect a potential bridge hack, right? And I wonder in zero knowledge if it's not a lot more difficult to detect when a bridge
Yeah,
is
yeah.
compromised.
That's a good question. I don't know.
Okay.
Does your system also have like any read limits? So like for regular bridges, very common method for minimizing the impact of hacks is to like set a maximum withdrawal for like every day, like 6 million USDC or something per day.
We don't have, yeah, so this is all customizable. You can totally run your own smart contract on top. Right now we have like deposit and withdrawal limits per account. Other types of limits mentioned, like we're certainly exploring these identity-based systems. So like proving that you still have to be in, say, an identity set in order to transact. But yeah, nothing beyond that right now. Cool. Thanks again for your time, and thanks for the good questions.